Welcome back. Today we're going to talk about L'Hopital's rule with limits. So all of you who desperately wanted to use L'Hopital's in the limits and I was making you do it through algebra, you are ready. You can now use L'Hopital's. Now there's a couple rules to this that we're going to go over, and then there's a couple that are very AP specific. So if you recall over here, L'Hopital's rule says that if you have a limit as x approaches a of a fraction like this, and you end up with either 0 over 0 or infinity over infinity, so it has to be these specific indeterminate forms, then the limit as x approaches a of f of x over g of x is the same as the limit of f prime over g prime. And we usually use a little h or an LH over the equal sign to demonstrate that we've used L'Hopital's rule in our problem. So the first thing that you're always going to want to show for the AP, especially for free response, obviously showing your work for multiple choice matters a lot less, is you need to show first that your limit satisfies one of these L'Hopital's rules. So the way that you do that first is you try just plugging in the number to the limit. So in this case, we'd say ln of 3 minus 2 over 2 times 3 minus 6 is equal to ln of 1 over 6 minus 6, which is 0 over 0. So you have to show that you have one of these two rules before you're allowed to use L'Hopital's, and you have to do it not just in your head, but you have to show the work for it on the free response page. So once you've done that, then you are allowed to use L'Hopital's rule. We put our little h above the equal sign to show that. It's the limit as x approaches the right-hand limit at 3. We end up with our derivatives, which would be, in this case, 1 over x minus 2, since the derivative of ln is 1 over x. Chain rule creates a derivative of 1 for the denominator, so we don't need to worry about that, over 2. And now we can simplify this. I would drop the x minus 2 into the denominator, because this is the same as 1 over x minus 2 divided by 2, or times a half. So that's the limit as x approaches 3 from the right of 1 over 2x minus 4, which we can then again plug 3 into, and we end up with 1 over 2 times 3 minus 4, which is 1/2. Now, most of these will feel pretty familiar. Just make sure that you're showing which indeterminate form you're using in the homework before you start using L'Hopital's in the problem. What you maybe remember also is that there are certain indeterminate forms, like all of these, that do not use L'Hopital's rule. So indeterminate forms 0 over 0 or infinity over infinity are fine. However, if you look at number 2, we have the limit as x approaches infinity of e to the negative x times root x. So that if we consider these separately, we end up with 0 times infinity. This is not one of our L'Hopital's rules, so we need to rearrange it and then show that it satisfies L'Hopital's. One of the most common ways that we would do this is the limit as x approaches infinity of root x over e to the x, because then you end up with a fraction, and then you've dealt with the negative exponent. And when we plug in for that, we do end up with infinity over infinity. So now we have shown that we can use L'Hopital's. So the derivative of root x is 1 over 2 root x, and the derivative of e to the x is e to the x. I'll use similar methods to simplify as we did in problem number 1, and we end up with 1 over 2 e to the x times root x. And if we plug in infinity for that, quote unquote plug in, you get 1 over infinity. And this feels like, oh, this maybe is an indeterminate form. It feels weird. That's fine. Just because it has infinities and zeros in it doesn't ever mean that it's going to be indeterminate. There's several indeterminate forms here, and then there's several determinate. So if I have 0 to infinity, still 0. Like, there are ones, just because infinity is involved doesn't necessarily mean that it's indeterminate. So make sure you're referring to these if you're stuck or confused, because it might just be one of those. Here, 1 over infinity is 0, because it's 1 being divided by a very large number. 1 divided by a million, if you type that in your calculator, real close to 0. Now, the last one we're going to look at here is a very famous limit that it's helpful, honestly, just to memorize if you have it memorized. If you don't, we can go through a way of solving it. The first thing you're going to end up doing is plugging into C. You then get 1 plus 1 over infinity to the infinity, which would be 1 plus 0 to the infinity, which is 1 to the power of infinity. Now, I'll tell you this. This might feel determinate. You're like, oh, it's 1 to a power. That's 1. Well, if you go to our table up here, you'll see this is actually one of our indeterminate forms, because something to an infinity power should be infinitely big, or 0 if the number's less than 1. If it's equal to 1, it sometimes can be kind of odd. It can, what we call converge, which means it's going to end up as being a number that's not 0, not 1, and not infinity. And the way that we show this is we try setting this equal to y. So y is equal to 1 plus 1 over x to the x. And then what we end up doing is solving like we normally would, where I'm going to take the natural log of both sides and then bring the exponent down out front. So x times the natural log of 1 plus 1 over x. Now, we're still interested in the limit here, so I'm going to take the limit as x approaches infinity. Now, the limit of ln of y stays ln of y because it doesn't actually have an x. Like, whatever x is doing doesn't affect what y is doing, so it's just going to stay ln of y, is equal to the limit as x approaches infinity of x times the ln of 1 plus 1 over x. And now, when we plug in our infinity, we are going to end up with infinity times ln of 1, which is 0. So we have a very similar situation to our last problem, where we're going to turn it into a fraction. And the way that I'm going to do that is I'm going to say, well, this is ln of 1 plus 1 over x all over 1 over x, because multiplying by x is the same as dividing by its reciprocal. Now, when we plug in, we get ln of 1 over 1 over infinity, which is 0 over 0. So we've shown we can use L'Hopital's. And when we do that, we end up with the limit as x approaches infinity of 1 over 1 plus 1 over x times, because we're using the chain rule, negative 1 over x squared. And in the denominator, we have negative 1 over x squared. Oh, this is great. Cancel, cancel. And we're left with the limit as x approaches infinity of 1 over 1 plus 1 over x, which when we plug into infinity equals 1. Now, before we circle 1 and you're like, Miss Ross, we told you 1 to the infinity power is just going to be 1. We're not done. Because remember, this whole side here doesn't equal y. It equals the ln of y. So what this tells us here is that 1 isn't equal to the function we're interested in. Ln of the function we're interested in is equal to 1. So then if I want to get y by itself, I have to raise it to e on both sides because we want to get this function. And so now we know that 1 plus 1 over x to the x as x approaches infinity is equal to e. Let me know if you have any questions about L'Hopital's or about anything that you've seen today.